Hey there, welcome to the physical geography. This class is about the hydrologic cycle, part of the hydrosphere. And what we're going to do is first see the whole hydrologic cycle, how it is all shaped together and fits together. And then we're going to look in detail at many of the parts of it and see how they work, and also talk about how they fit into the larger picture. So we can start with a quote and a river. So on the bottom, you have a picture of the James River, which is the biggest river in Virginia and its important role in American history. It's where Jamestown was founded, the first British colony in North America, an area which later became the United States. And at the top, you see a quote from Heraclitus, the Greek: "No man ever steps in the same river twice, for it's not the same river, and he's not the same man." So Heraclitus understood that life is dynamic. Things are always changing. And so that's going to be very evident as we look at the hydrologic cycle. We're going to see that it's a good example of how things are always changing, because we see lots of motion, lots of interaction between the parts of the hydrologic cycle. We'll see water go from a liquid state to vapor, go to ice, and back and forth. We go from the ground, the lithosphere, to the atmosphere, and then even into the biosphere. We'll see water in species as well as in the air, as is in the ground, and in the oceans too. So all the spheres are connected through water. So let's take a look at the hydrologic cycle, the water cycle. It's a continuous cycling of water from the earth to the atmosphere and back again. So the water keeps moving around in a cycle between the earth itself and then the atmosphere. And the sun is driving all of this cycle. The sun is behind the whole thing. In elementary school, we learned that, there's evaporation, condensation, and then precipitation, the three basic steps of the water cycle. But we can go a little bit further than that here with the basic steps in the hydrologic cycle. So first, it's basically evaporation, but we can expand on it a little bit. We have evapotranspiration. We're just going to add, besides the regular evaporation that we have out of the water sitting on the earth, liquid water, like in lakes and oceans and ponds and rivers and things like that. We also have evaporation out of plants, which takes place out of their leaves. Okay, so that's called transpiration, evapotranspiration. Let me just show you a little bit about how that works. The transpiration is the loss of water from plants through evaporation out of their leaves. And you can see on the left that under the bottom of a leaf, there are these openings called stomata, and that's where the moisture leaves the plants through evaporation. So transpiration is just a type of evaporation out of plants' leaves. And with transpiration, it's a very important role, especially in rainforests, because if you're like me, I always wondered, where is all that rain coming from in the Amazon, right? Because a lot of the Amazon is deep inside South America. I mean, the continental effect means places that are far from the ocean tend to be drier, but apparently it doesn't apply here. So where's it all coming from? And part of the answer is that the Amazon rainforest makes its own rain. And just for perspective, 1 acre of corn transpires or evaporates off of its leaves 3,000 to 4,000 gallons of water per day. That's a lot of water. So transpiration is a very important part of the hydrologic cycle. So in the diagram in the center, you can see evapotranspiration is kind of summing up all that evaporation from all over the land and also from plants as well. The second step in the hydrologic cycle, convection. We know about convection from our climate section, like the Hadley cell. It's a loop, right, of rising and falling, for example, due to a heat source. In this case, the heat source is the sun. It makes air rise, and that's what's going to take that evaporated water in the air upwards, put it up there instead of down here. So that's what makes air rise. That's convection. Then we're going to have condensation. That's when the water vapor, once it gets high, it's going to cool off up there because the air has to use heat to rise. Remember, heat and energy are the same for gases. So by moving up, you use up heat and you cool off. By the time it gets there up high, it's very cool, and then it has to condense, right? The air molecules get tighter together. When they get tighter together, there's no more space for the water between them, and therefore the water has to get squashed together into droplets and will condense and then fall as rain, or even freeze and fall as snow or sleet. And that's going to be precipitation, when that liquid or frozen water falls to earth. And the last step is collection. When the precipitation falls, where's it going to go? Well, it's going to fall eventually into oceans, lakes, streams, rivers, etc. If it goes onto the land, it could end up in the ground underneath. We'll talk about underground collection as well. You can store water in the ground as well. We'll talk about that. Okay, so evapotranspiration, convection, condensation, precipitation, and collection. Those are the 5 steps in the hydrologic cycle. Hydrologists are people that study water, and they make water budgets. They calculate all the water coming in and out of an area. It's basically like an accounting system for water. And out of that, they produce what's called a water balance. It's the ratio of water gained to lost in that area. It could be a farm, it could be a city, it could be in a park, something like that. And it's good to know because, for example, if you're in an agricultural area and you're seeing a loss of water from the aquifers, the underground water storage that's used for farming, and it's not being recharged enough by the rain, you can see that the entire environment there is losing water. And you want to know that to plan the future. Fresh water is water that has low or no salt. For example, straight out of the sky from rain, or often found in rivers and lakes. Brackish water is a mixture of fresh and salt water. So brackish water is sort of like semi-salty water, kind of salty water, but not quite fully salt water. And then salt water is the water that's seawater that's found in the oceans. So what you see in the diagram at the bottom left is kind of the gradient or scale between totally fresh water, pure water with zero salinity. And as the salinity rises, you get to sort of semi-salty water, brackish water, and then out to seawater out here. So the river has fresh water upstream, and then the brackish water sort of in the middle in this estuary, which we'll learn about later. And then at the end is the ocean environment, which has the salt water. Fresh water, like we said, has not only low salt, but it also has low solids in general. There's just not much stuff in the water besides water. And it's only 3% of the Earth's water. Most of that is frozen in the cryosphere, the frozen part of the world. So that only leaves a very small percentage for us to have in rivers and lakes and things like that and to drink. But yet that small percentage is incredibly vital for the world's animal and plant species. The cryosphere is all the frozen water in the world and in its climate system, meaning Earth itself and then up in the sky if it's frozen up there, coming down as snow, for example. And the cryosphere is all fresh water. It's all fresh water. So we have glaciers, ice sheets, sea ice, et cetera, all frozen. And it's important to realize that if it's in the ocean, for example, when water freezes, even if it started as salt water, when it freezes, the salt gets pushed out, actually goes into the ocean from sea ice, and then it drops down to the bottom and makes the water even saltier below. Okay, so when you see all that ice on the ocean or icebergs, whatever it is, just think there's no salt in there. It's been squeezed out. So then seawater or salt water is obviously high in salinity. It's the kind of water you find out in the ocean. And because it's got much more dissolved solids in it, it's therefore much heavier than fresh water. Surface water is any water that's above ground. That's a big category. So any kind of rivers, lakes, oceans, wetlands, they're all called surface water. And we can contrast that with groundwater. There's a whole world of water under the ground. And we'll be talking more about that in detail. So groundwater is the water beneath the Earth's surface, in the rocks, in the soil, in the pore spaces, the little gaps, the nooks and crannies, and fractures within the rock formations. Okay, so a very large percentage of the fresh water in the world is under the ground. More specifically, one place that groundwater is collected or stored is called an aquifer. Aquifer, that's a permeable layer of underground rock, as you see in the diagram, that becomes a reservoir that stores and transmits groundwater. Okay, so it's a little confusing because the aquifer is not actually the water itself. The water is just groundwater, but the aquifer is the rock with the holes in it, like Swiss cheese, that holds the water. Okay, so aquifer, the word comes from aqua, meaning water, and fer, like to ferry something is to carry it, ferry it along, or transfer, you carry across. So fer means carry. So it's a water carrying rock, an aquifer. You can see in this diagram, there's two basic types of aquifers. There's a confined versus unconfined. So if you look at the bottom first, the confined aquifers are basically sealed down there by a layer of impermeable rock on top. Rock, clay, something that's going to seal it in so that the water from the atmosphere, from above ground, the rain and precipitation is not going to be able to get in there and refill that aquifer in the confined aquifer because it's just sealed down there. Some of the oldest, if you notice, they give the time that the water is spent underground. You can see it says days, years, centuries, millennia. And so if it's millennia, it means thousands of years. Sometimes they call that fossil water. meaning the water in deep, deep aquifers that are confined. And by that, they mean that some of that water is super, super old. And so when you take it out, the problem is people use that water. Sometimes they stick pipes down there and pump it out to use for farming or drinking water. The problem is it's not going to get recharged anytime soon. But that's a confined aquifer, and that means it's not open to rain and precipitation. So it's not going to get recharged. That's a big issue for example, the American Midwest is losing a lot of water underground, or American Southwest in Arizona, Southern California. By contrast, an unconfined aquifer on top is open to water from the atmosphere. It doesn't mean that the water just goes right in and hits it immediately. It means that water from the atmosphere, from precipitation, when it hits the ground, eventually it can percolate downwards into the ground and it can end up there because there's no seal layer of impermeable rock on top of this unconfined aquifer. If you get a bottle of Fiji water, which is a very expensive brand of mineral water, that's actually water from aquifers, right? From aquifers that are inside of these volcanic islands in the Pacific, the country of Fiji. And being down there inside of this giant pocket of rock underground, it accumulates a lot of minerals in it from the rock that surrounds all the water, like Swiss cheese. And so that's one of the reasons people buy it, is because it's so high in minerals, in particular silica. And silica is what helps your nails and your fingernails grow. If you drink a lot of Fiji water, you'll start noticing your hair and nails will be thicker, seriously. Or any other source of silica. So that's what makes it different. Let's talk about streams. Streams are bodies of water that flow continuously, flowing water in a continuous manner. So that would be like rivers, creeks, and this is what we call streams. Okay, so streams is both a general category, just streams, including rivers, creeks, and also a particular thing called streams, kind of a middle level between creeks and rivers. Anything related to streams, to water flowing continuously, we call that fluvial. Fluvial is really related to rivers. Okay, so if you see like fluvial science or fluvial systems, it's a fancy word for rivers and streams. Streams can have tributaries. Tributaries are streams that flow into larger streams or lakes, right? So you have a stream flowing into another stream, like branches, right? So, and then tributaries can have tributaries. Let's take a look at the Amazon here. So you see Macapá over here in Brazil. You can go down the Amazon like this. But then you see there's lots of tributaries. The Amazon has tributaries like the Japura, for example, right here, which then has its own tributaries like the Apaporis right here and all, et cetera, the Putumayo. Many, many tributaries and then tributaries of tributaries. Okay, so there's actually a whole science called stream ordering. If you want to look that up, it's interesting. And they try to figure out, okay, which are the tributaries of the tributaries of the tributaries, and put them all in the right levels, kind of like smaller to medium to larger branches on a tree, and see how they all are ordered in a hierarchy, sort of a hierarchy of branches, a hierarchy of tributaries. So let's get into the weeds a little bit. There's three types of flowing water flowing. First is the water we've just been looking at. The water flows through streams. That's called stream flow. Then there's water that doesn't flow through streams, but flows across the surface of the earth, like across, for example, a soccer field. If it gets soaking wet during a flood or something, across your lawn, whatever it might be. We call that overland flow in the picture, or surface runoff. Okay, that's not surface, not across a river, not across a stream, just across the ground itself. And that happens when the ground gets so saturated that there's no more space for water to infiltrate down into the ground, and so it just piles up on top and slops across at overland flow. Then finally, we got throughflow. That's water that's flowing, but not above the ground, but underground. See in the picture there, the red arrow, it's got into the ground first, and then once it's down there, it flows across through the ground. Okay, so we have three types of flowing water: stream flow in rivers and streams, overland flow across the ground surface, like across your lawn, and then throughflow, water flowing beneath the ground, but sideways. So all we're talking about here is horizontal flow of water. So this surface water and groundwater are constantly interacting, right? They're very much connected in the water cycle. And the water can go from the surface to the ground and back many, many times, and then up into the atmosphere too. In a river, like on the left, a stream system, you have water actually goes from a river, for example. Sometimes it can seep out of the river through the ground, out into the groundwater around it. And then other times, the water in the groundwater can seep into the river, right? So if you see the arrows on the left over here, it's showing you how at certain times rivers can gain water from the ground around it, and other times those rivers can lose water into the ground. There's actually technical terms called a gaining stream and a losing stream for those two types of situations. And you see also on the right, you see the ocean itself. The ocean itself can take in water from groundwater through the floor of the ocean. So in both cases, it's the same idea. On the left, you see water can seep from the groundwater into rivers, or it can seep from rivers into the groundwater. And on the right, you can see that water can seep from the groundwater into the oceans, or it can seep from the oceans into the groundwater. Even saline water, the salt water, can do that on the right. Lakes are bodies of standing water that are in some basin. A basin is like a bowl shape, a dip in the Earth's surface. There's many reasons for causing lakes, from anything from glacial erosion that scours out these bowl shapes at the bottom of glaciers from past ice age, for example, to volcanoes that erupt and they blow out all the lava from the middle and then there's nothing left and there's a bowl shape. Or just between mountains, but in the valleys between mountains, it creates a V shape and the water collects in there. So there's many reasons why you could have a lake, but they all have the same basic idea of collecting water. If you remember, we said that fluvial is a fancy word for anything to do with rivers. And here we have another fancy word, lacustrine. If you see a paper about lacustrine systems, it just means related to lakes. Lakes are so good at collecting water, of that function of collection within the hydrologic cycle, that humans often build artificial lakes and ponds in order to collect water, especially in areas that are susceptible to flooding. So here you see this massive project in Anhui, China, where they built not only a lake, but also a solar farm that floats on top of that lake. We looked earlier at three types of horizontally flowing water going this way across the land. And now let's look at three types of water going this way, going vertically downwards, descending water. First, we have infiltration. If you see in the diagram there, infiltration is the process of water simply entering the soil, right? So it's up here, it's outside the land, it goes into the land, goes into the soil. Okay, just like a spy infiltrates, the foreign service or something like that. You infiltrate from the outside in, right? Inside into the soil. And then once it's in there, then when water is flowing downward through the soil, through gravity, not just entering, but then once it's in there, call that percolation. Percolation. Think of like coffee. When you put water into the coffee maker, what does it do? It drips down through the grinds. It makes its way through, right? And that's percolation. Okay, so percolation is the water flowing downward through gravity through the soil. And finally, interception. That's when water is intercepted. It's blocked by something else, the vegetation on the top layer, from entering the soil. Okay, so that could be from the leaves. If you have a rainforest, you have lots of leaves and branches, and those stems and stuff, they block the water so it can't infiltrate. And many times we want to slow down the infiltration and percolation of water and even intercept it in order to prevent floods. And one thing that's very, very good at doing that is wetlands. Wetlands are areas that are covered or saturated in water for all the year or a significant part of the year. So we're talking about things like swamps, marshes, mangroves, bogs that have in common that they are able to survive and thrive underwater or in deep water for a long time. Okay, so it's interesting because wetlands were sort of like looked at as a nuisance in the past up until recent decades. And then people realized that instead of paving them over and just cutting them down, getting them out of the way, there's a real value to wetlands, and they started to build them up. You have wetland restoration projects along coastlines, for example, and rivers, and then wetland creation projects, not just restoring wetlands, but actually putting wetlands in places they didn't even exist before. And the reason for that is that wetlands are very, very valuable for both the environment and for people. They act like a sponge. So when you have floods, for example, in a hurricane or storm surge, you have the wetlands there acting like a sponge along your coastline that really reduce the height of the waves and storm surge and also the impact on the city. They put this big buffer, this big sponge between the city and the water. Secondly, wetlands have a great ability to detoxify water. It's amazing. You can put some of the worst chemicals into water and wetlands will detoxify them. And then third, being very, very dense, they are a great habitat for fish and also for birds and other wildlife, turtles, etc. So wetlands, we're talking about places like the Everglades in Florida. These are really, really good for ecosystems and for people. Here's an example of China, Sanya, China, where they created a mangrove park. Mangroves are the special kind of wetland vegetation that has sort of like, looks like it's on stilts almost because its branches come out of the water. And it has a special ability to mangrove vegetation to remove the salt from water. So these are actually like trees that can live in salt water. It's the only trees that can do that. And so mangrove trees in particular, of the same type you find in the Everglades, have become a very, very popular way to restore or create new wetlands. And that's what you see in this picture. They put an entire mangrove park around the city to soak up all that floodwater around its rivers. China has real problems, serious problems with river flooding. And now they're trying to go the other way. There's a whole thing, you can look it up, called the Sponge Cities movement, where China is trying to have its cities absorb water better, collect it, and then direct it where they want it, and then use it for people instead of just being buffeted by rains and floods. So as we talk about water running off through an area in many different ways, through streams, through groundwater, and through overland flow, a particular area where all that takes place is called a watershed. A watershed. It's also known as a drainage basin. You see that word used often. And the dividing line, kind of the sideline or boundary around a watershed region, is that yellow line that you see in the map. It's called the drainage divide. Okay, it's what divides one watershed from the next. So let me highlight a point of confusion. A lot of times people get confused because you see the word watershed and you might naturally think that it's a body of water, right? Because it says watershed in it. And it is not. A watershed is not a body of water. It's not an ocean, a river, a stream. It's not a water collection. What a watershed is a place on Earth, a region, like the region inside the yellow line, which includes land, water, anything in there. It's a zone where all of the flowing water in there, whether it comes in the ground, on the surface, whatever, ends up in the same final point. Okay, no matter where it goes. It's talking about over, could be tens and hundreds of years, but ultimately ends up in the same endpoint, whether it's a river, stream, lake, etc. Okay, that's what makes it a watershed, the common endpoint to all the water that flows in that region. Okay, so you can see all the blue arrows that are the water flowing down from the mountains and then across the streams and farms and people's property, out of lakes, whatever it is. It's all going to end up in that main river in the middle, and that's going to flow out to whatever that is, a lake or sea, etc. Okay, all to the same endpoint. So just to reinforce it, a watershed is not a body of water. It's not a body of water. It's an area that you can map on the Earth. It's got a boundary, like you can draw a line on a map, the boundary around it. Okay, a zone. You can think of a watershed like a funnel. See on the right, you have a funnel, and just like a funnel, anywhere you have water poured into that funnel, it ends up coming out the same endpoint. It's the same thing with the watershed. Anywhere it rains, anywhere it snows, anywhere Farmer Brown hoses, his corn or whatever, it goes into the ground and flows through. Anywhere some factory dumps water into whatever, it ends up flowing into that main river and out to the main body of water, the ocean or lake beyond it. In that way, watersheds are unifiers. They connect the people in them because they all share the same watershed. And so we have to look out for each other as neighbors and fellow citizens to see, okay, how are we affecting the watershed and how are we all each contributing to the cleanliness and safety of the water in that watershed. As we saw, watersheds are the areas where water flows into the same endpoint, and many times that endpoint will be through an estuary. So an estuary, in simple terms, is where the river meets the ocean. Okay, where the river meets the ocean. Basically, rivers come down to the coastline, and the ocean's over here, and finally they meet. And there's that kind of middle area here where it's kind of the end of the river and kind of the beginning of the ocean, and that's the estuary. Okay, so you get fresh water from the river coming through, but then it's ocean water on the other side, which is salty. So what kind of water is in the estuary in the middle? It's going to be kind of fresh, kind of salty. Oh, that's brackish water, right? We said earlier, brackish water is water that's a combination, sort of semi-salty water. That's the kind you find in the estuary. So just to be clear, that's a scientific term, but we know estuaries from their more common terms on maps: bays, coves, harbor, sound, stuff like that. So the Chesapeake Bay is what's on the right there, and you can see Virginia, and you can see Virginia has the James River, the Rappahannock River, the Tappahannock, all these different rivers, and Pennsylvania, the Susquehanna, et cetera, et cetera. All these rivers that contribute to the Chesapeake Bay in the middle, because the Chesapeake Bay is the semi-enclosed body of water, because part of the Chesapeake Bay is open to the Atlantic Ocean and the other side is open to all of those rivers. Okay, so many, many rivers are contributing to that Chesapeake Bay estuary. Chesapeake Bay is, in fact, the largest estuary in the United States. The second biggest is Puget Sound in Washington State. And really, it's amazing because the Chesapeake Bay region, or we could say the Chesapeake Bay watershed, which is what you see on this map, is home to 5% of America. It's truly amazing. From Philadelphia to Baltimore to D.C. to Richmond and Southern Virginia, it's all part of the Chesapeake Bay watershed. And again, what that means is that all the water from wherever it comes from, across farms, surface runoff, across your lawn, it all flows out from those rivers into the Chesapeake Bay, which is then open to the ocean on the other side. That's what makes it an estuary. Estuary is open to the ocean on one side and rivers on the other. So if you look closely at the map, you'll notice that the Chesapeake Bay has rivers flowing into it from 6 different states: Virginia, but also Maryland, D.C., Delaware, Pennsylvania, and New York. So it really is, that watershed connects many different communities. And that requires interstate management. Obviously, it can't just be one state managing it. And so that requires that cooperation across state boundaries to manage the Chesapeake Bay watershed. So we started with the James River in Virginia and the origins of the United States, and I figure we end there too. So this is a map from 1612 by John Smith, one of America's earliest pioneers. He was an explorer, British explorer, who was one of the original founders of Jamestown in 1607. This is a map he made of that region, the Chesapeake Bay, 5 years after Jamestown was founded. And it is of the Chesapeake Bay. Now, this map is actually turned 90 degrees. So it's really, the Atlantic coast looks like this. You know, one normally see it like that going down the coastline, but here it's like turned sideways. So if you look closely, it says the Chesapeake Bay in 3 parts here, or 4 parts: Chesapeake down through the middle here. And then this part out here in the Atlantic, kind of the tidewater right outside of that area there, they call it the Virginian Sea. And up here, right in there where that pointer is, you can see Jamestown, 1607, it was founded. Okay, but what you notice is that this area has many rivers, right, that flow out into a body of water, an estuary, Chesapeake Bay, which is then open to the ocean on the other side. Okay, and that's the definition of an estuary. This is a very rich area in wildlife at that time. Estuaries get the best of both worlds. They get river species and they also get ocean species. If you live in the area of the Chesapeake Bay, you know it's famous for seafood and crabs and stuff like that. So these original colonists, they had a field day going around shooting ocean birds. They had birds left and right. They had fish and oysters and clams, crabs, so much food that was available because all of this was, kind of marshy, swampy wetlands and stuff around the edges of the Chesapeake Bay. And there's just tons of wildlife in there. So there was no shortage of fish and fowl, right? No shortage of birds and fish in there for these guys to eat. I remember this is a time in British history when food was scarce. You had too many people in Britain for the amount of food that they had. People were eating dogs sometimes, and then in that era. And to come to the New World here and have so much wildlife available to you in the wetlands of the Chesapeake Bay, and the fish and the seabirds and the clams and oysters and everything, crabs, was just a real total contrast from the world that they came from across the Atlantic. So that's a look at the hydrologic cycle. We saw the big cycle, how it all fits together, and then we looked at many of the parts of it and saw how they play their role within the larger cycle. And we also saw some examples of how humans work to sustain the environment within the hydrologic cycle and also work to sustain human communities.